Butter is a saturated fat, and oil an unsaturated fat. But when it comes to the chemical compounds, what do the terms saturated and unsaturated mean? Today's lesson is on alkenes and alkynes, hydrocarbons with 2 and 3 bonds. So alkenes and alkynes are hydrocarbons with double and triple bonds. Hydrocarbons with double bonds are called alkenes, and hydrocarbons with triple bonds are called alkynes. And again, you'll find that information in your data booklet. These compounds are named in a similar way to alkanes using prefixes to indicate the number of carbon atoms, but their names end with "ene" and "-ine. Alkenes would be ethene, propene, butene, and so on. Alkynes would be pentyne, hexyne, heptyne, continuing on to decyne. If we look at the general formula for alkanes, we have CnH2n plus 2. The general formula for alkenes is CnH2n. And the general formula for alkynes is CnH2n minus 2. And this information is in your data booklet. The type of bond affects the chemical properties such as reactivity and physical properties such as boiling point, melting point, and solubility. A compound will be more stable if it's larger because there's more carbon-to-carbon bonds to break up during a reaction, or if it does not contain multiple bonds. So alkenes and alkynes with double or triple bonds are relatively easy to break because there's more hydrogen bonds that are a stabling force in a molecule. So more stable compounds have a higher melting and boiling point, are less reactive, and are more likely to be found in solid form. So when we say like dissolves like, so polar solutes will easily dissolve in polar solvents. So water is polar, so it will easily dissolve ionic compounds, acids, and polar molecular compounds. Alkanes, alkenes, and alkynes are nonpolar, so they dissolve better in a nonpolar solvent such as oil than a polar one like water. So we can dissolve alkanes, alkenes, and alkynes more in oil than water. Naming the alkenes and alkynes is similar to naming alkanes. We use prefixes to indicate the number of carbon atoms, and the suffix indicates the type of bond. Since the location of the multiple bond affects the chemical and physical properties of the compound, we must also specify the location of that double or triple bond. So pent-1-ene indicates the double bond is located between the first and second carbons of the parent chain, where pent-2-ene indicates the double bond is located between the second and third carbons of the parent chain. So pent-1-ene versus pent-2-ene have different carbon locations, double bond locations. However, naming rules for alkenes and alkynes are similar to alkanes when it comes to the branches. We want to find the longest continuous chain of carbons. For alkenes and alkynes, the parent chain must contain the multiple bonds. So our double or triple bond should not be in any of the branches. So we have 5 carbons pent, the double bond ene, and it's between carbons 2 and 3. So we want to determine the location of the double or triple bond after the carbons are numbered. So for alkenes and alkynes, we actually start numbering from the end closest to the multiple bond instead of the branches, because we want that to have the lowest possible number. So after that, we identify any branches and their location. So this is a 2-carbon branch. So it will be ethyl because there's 2 carbons, and again, that YL identifying that it's a branch. So then we're going to write the complete IUPAC name, the number of the locations, the branch name, the prefix of the carbon chain, and then the suffix of the parent chain and the location of the bond. So it's pent with a double bond between carbons 2 and 3. So it would be the second bond in the branch. And there's a 2-carbon branch on the third carbon. So we have 3-ethyl pent-2-ene. So now we're going to name this following compound. We want to find our longest branch, which is going to be 1, 2, 3, 4, 5. So it's going to be pent. Our triple bond is located on our second bond between 2 and 3. So pent 2, and it's a triple bond. So we're going to go -ine. And then we have a methyl single carbon branch on the 4th carbon. So we're going to go 4 methyl pent-2-ine, identifying that there's a triple bond between carbons 2 and 3. To draw alkenes and alkynes, we're going to follow the same steps that we did for alkanes. We're going to start from the back and move forward. So we have hept-3-ine. So that's our parent chain. It gives us the type of bond and the location bond. So it's a 7-carbon parent chain, and it has a triple bond on the 3rd carbon. So we're going to draw that skeleton. So 7 carbons, triple bond at the 3rd carbon. So the maximum bonding capacity of carbon is 4, so that's going to affect the number of hydrogens because we don't have any other space for hydrogens on carbon 3 or 4. So our next step is to draw any identified branches. In this case, we have 2,5-dimethyl. So we have 2 single carbon branches on the 2nd and 5th carbon. So we're going to draw them in. So we've drawn them in down to the bottom. We have a methyl branch on the 2nd carbon, a methyl branch on the 5th carbon. And then lastly, we can fill in any extra hydrogens, remembering that we have a maximum bonding capacity of 4 bonds. Now we can look at isomers. So isomers are compounds containing the same number of carbons and hydrogens, but in a different arrangement. So we can look at heptane C4H16. There's only one way of drawing that one. But we can have dimethylpentane. So isomers have the same formula, but different structural diagrams. So both of these have 7 carbons and 16 hydrogens, but in a different structure. So when we also look at alkenes and alkynes, these are 2 organic compounds that are said to be unsaturated. So these are unsaturated because they're not holding as many carbon ions as possible. So in addition to hydrogen molecules, the addition of hydrogen molecules to an unsaturated hydrocarbon is called hydrogenation, and it results in a saturated hydrocarbon. So all single bonds, and every bond is being filled. The term saturated means full, so alkanes are full of hydrogens, where alkenes and alkynes are not. Some of those carbons are double and triple bonded, and those bonds are taking the place of some hydrogens that could be added. To become saturated, the double or triple bonds must break, and the hydrogen atoms must take the place of that multiple bond in an addition reaction. So there always must be enough hydrogens in addition reaction to fill the 2 bond sites. Alkynes have triple bonds, so 2 hydrogen molecules or 4 hydrogens are required to fill the bonding sites. Alkenes and alkynes also tend to react readily when other small diatomic molecules such as the halogens. So like with hydrogen, some of the bonding sites once occupied by multiple carbon-carbon bonds become filled with halogens. So in the presence of chlorine gas, ethene can have 2 chlorine molecules bonded onto those sites. Often, we use the terms saturated and unsaturated in combination with fats. So animal fats and plant oils are a good source of energy and calories, and an essential nutrient. Fatty acids are organic molecules made up of a long chain of carbons with a COOH group at the end. The other end has a methyl group. The structure of a molecule affects its physical and chemical properties. So oils tend to be unsaturated fats, and they contain double or triple bonds, which causes the molecule bend, which is why we can pack them tightly together, and they can be in liquid form. Fats, either man-made or from animals, tend to be saturated fats containing only single bonds. Remember, they'll be full of hydrogens. This causes the molecules to be straight so that they can pack tightly together in that pattern. This is why they tend to be solids at room temperature. The solid state and the fact that they're alkanes containing all single bonds means they're very stable, which means they have high boiling points and high melting points. Monounsaturated fats have 1 double bond and 2 fewer hydrogen than a saturated fat. So mono meaning 1 unsaturated fat. Polyunsaturated fats have more than 1 double bond, so even fewer hydrogens. Generally, unsaturated fats are better for the body, even though they both have the same caloric components. So hydrocarbons with double or triple bonds react more easily. It's less work for our body to break down. Saturated fats are harder for our body to break down, so they tend to stick around in our arteries and veins. We do need fats, however, and essential fatty acids are fats that our body can't make and are found in certain foods. So omega-6 fatty acids are found in margarine, processed foods, corn, and soybean oil, but these aren't essential. They are essential for clotting. Many people eat too many omega-6s, so we only need a small amount of them. Omega-3 fatty acids are found in some fish, flaxseed, and enriched eggs. And these fats have the opposite effect of omega-6s. They reduce swelling and slow blood clotting. So it's important to have a balance between the two of them. You don't want only omega-6s, but you also don't want only omega-3 fats. Now, cis and trans refer to different 3D arrangements of a certain molecule. Cis fats are naturally occurring but can be made into trans fats through a process called hydrogenation, which involves the addition of extra hydrogen ions. Now, because trans fats are synthetic, they're the hardest for your body to break down, so they're the worst kind of fats. And many processed foods have now removed trans fats from their processing method. So once they're in solid form, trans fats oils, once they've been turned into solid form through hydrogenation, are easier to work with. They're typically softer and easier to spread than typical animal fats. So spreadable margarine was a trans fat originally, but through processing procedure, they've largely changed the manufacturing. So we need less trans fat to have the same effect on a food, so they qualify for a low fat label, even though the fat is much worse for you. So one location where we can still find a lot of trans fats, incidentally, is in microwave popcorn. So it's important to check food labels so you can identify how much trans fat is in there. Food manufacturers are allowed to put up to 0.5 of a gram of trans fat and still label it trans fat free. So you want to check your labels for partially hydrogenated oils, which was when they've added hydrogen to oil to turn it solid. I hope you enjoyed today's lesson. Take it easy.
If you enjoyed this video, check out our website online.plrd.ab.ca and visit us on Facebook, Prairieland Online Academy. You can find out all that's going on with Prairieland Online Academy.